everyone. Thank you for joining my talk today. A quick intro about me. This is Sri, and I'm with HCL Technologies. I've been in the industry for a couple of decades, wearing multiple hats. At present, I get to provide digital transformation solutions, especially in the AI and big data world, mainly through cloud for our customers in the ERS division. Before I start, I would like to remind you that I'm available for chat during the talk. So as questions arise, please click the chat button to submit your questions and I will be able to answer you. Every organization today is somewhere in the trajectory of AI journey, and all enterprises are now facing information overload with added complexity of business-specific language and domain-centric information processing. This presentation will explore multiple NLP and NLU techniques, state-of-the-art techniques, to augment those new business values for the use cases like summarization in the medical context, where the information is dense, complex, specialized content, and contextualization in domain-heavy segments like Aero, auto, industrial, banking, finance, insurance, and more. We will take these use cases and construct them as modern digital data augmented workflows and show you how AI is applied in the flow. Moving on to the next slide. 80% of the analyst time today is spent on 80% of the analyst time today is spent on analyzing and discovering the data or preparing the data. And only 1% of the unstructured data is being analyzed, if at all any. So because of the accelerated value chains in whatever we do today, data is at the front and center. And the first step to recognize here is the speed, the magnitude, and the non-linear nature of the disruption that the organizations are going through, where AI comes to a rescue. If you pay attention to the two use cases that I'm going to discuss today, one is about the intelligent clinical evaluation. It is about medical device reporting. Medical device reporting is a multi-step process. And if you are a medical device manufacturer today, complying to FDA and device regulation is a federally mandated exercise. It has multiple steps like deciding the intended use and the classification of planned devices, establishing the necessary processes, as well as resources, minimizing the risk, etc. One of the steps we will be discussing today is called clinical evaluation report, which are usually done by a team of medical writers and doctors mining through lots of information, and the outcome of that journey is to provide a report that demonstrates compliance for a specific deliverables. So we are going to go through the clinical evaluation process and apply AI to it today. When we apply clinical evaluation, the clinical evaluation report will have a lot of classification of the device, how novel the device is, the amount of clinical data on the equivalent devices already in the market, in the published literature. So doctors have to go through this and search through a lot of information first before they can arrive at a report. In the next 20 minutes, I'm going to walk you through three things. First, we are going to encode the technology as a business problem set here and provide an AI-driven outcome for that. The second one I'm going to do is codify the process of applying AI to that specific process like clinical evaluation and give you an algorithmic walkthrough of what we see as benefits in our approach. The third thing I'm going to do is apply NLP and NLU and decode business requirements to a series of AI-centric components, so you will see how the data flows through the journey. And I also want you to know that in this process, we are going to show you how we enable the customers to achieve their business objectives in a short time frame. When it comes to intelligent clinical evaluation, it takes around 4+ weeks today. So moving on to the intelligent clinical evaluation as a user story, you will be seeing a lot of boxes here, but the idea here is wherever there is a high demand for generation, we start with the goal of reducing the burden on the team of doctors and medical writers whose precious times are expended today on reviewing this and to arrive at a summarization. And they can focus on important tasks other than this manual task. In the next few slides, we will see how these different pieces fit together and emerge as a use case. If you observe each and every box here and every item within that encodes a workflow. If we zoom out a bit, a typical medical enterprise today will need to apply all these steps manually to create a clinical evaluation. We will see how to build an intelligent AI solution that compresses the time end to end. In essence, we are trying to improve the productivity in MDR submission and build efficiency for comprehending biomedical literatures, either by using the cognitive services or using the OCR technologies out there, or doing a machine learning, deep learning based NLP and NLU, and then providing assisted authoring. One of the end goal here is to apply the same methodology to scientific journals and other enterprise documents available from customers with AI generated comprehension and understanding. Moving on to the next slide, I just want to spend a bit of a time here on the architectural preview here. This is an end-to-end scalable, adaptable, flexible architecture with modular AI services that are reliable, repeatable, and renewable to new neural network architectures. There is always a renaissance in the NLP and NLU in the past 2 years, and we made our architecture to make sure it fits into the new journey as and when the new thing comes into the play. Let me take a minute to explain this diagram for you. If we go from bottom up, we are end-to-end GPU accelerated infrastructure when it comes to either development or inference for all these models. Thanks to the NVIDIA team, the power of DGX is really appreciated when we deliver the proof of concepts or the prototypes or the working product we have to the customers with fast turnaround time. And I also want to paint a different kind of picture for a moment, if I may. With all the changes that is happening in the AI, which are unprecedented, and the technology and the models are developing so fast, we would not have had the capacity to try anything new if not the DGX V100 boxes we have today. And if you go and see a little bit up, the cluster management, we have a Kubernetes cluster, and we also have some standalone clusters. Majority of our container instances run specific models today like PEGASUS, FLAIR, ScienceBird, or FAIR M2M100 for multilingual translation. From a programming language stack, we use majority, 99% of it is Python, a few of it is Scala, and some of it are Java. But we also have a tint of C#. And as well as from a web front-end perspective, we have a React and Node.js, and we also use Azure Cognitive, Q&A Maker, and Lewis. We use Rapids AI for Apache Spark. We also do PyTorch and TensorFlow. If I stay back a minute, we also have a distributed scale-out enterprise architecture where there are the web application, there's a voice-enabled application, secure API endpoints, and as well as a mobile application that supports this. There are 4 steps that I want to emphasize on from the previous diagram, which we will be discussing in detail today. The classify, recognize, validate, and author, where we 90% of the time use AI models to do the work for us. In classify, we use it to categorize, discover, mention, understand the events, and mask the data. In recognize, we tag them, link them, transform them, and do the named entity recognition on it. In the validation phase, we understand the similarities between the document, we rank them based on the comprehensive understanding of it, we summarize them, and also apply some specific domain task there. On the knowledge mining side, we do a cognitive search, we do active learning through Q&A Maker, one of the another Azure tool out there, and then we also do authoring and review on top of it. So in the classify stage, it all starts with a lot of published medical journals being ingested into the data pipeline. And what we do there is we extract them, we cleanse them, we pre-process them with the latest and greatest parsers, and provide that content in XML or JSON or structured format to classify, where we can categorize the mentions, the benefits, the limitations in that document for a given medical device procedure, the implications, or even finding a particulars like age group, gender, device, you name it. And then we also do sentence classification and opinion mining from it. In the discover phase, we do the adverse event detection and knowledge base extraction. On the de-identify phase, we do de-identify some of the PII and health information in it so that the information can flow downstream. On the classify and benefits, in classify, we have multiple items to go through. Benefits is one of them. The understanding of benefits is to identify in the given published medical journal how the device has some specific benefits, right? And we used bioclinical bird, Emily's bioclinical bird, which is a 12-layer bird model with an uncaged vocab. We prepared our own data set as a training set. It was a fun journey. We also used the LSTM model on the structured abstract, which is around 100K PubMed abstracts, to predict the probabilities, the results, the methods, the conclusions, background, etc. What you see here is just a representation of how we can identify the benefits from a given document or a set of documents. We also have algorithms to identify the limitations with zero-shot classifiers to initially start with, and then pre-train them with the 100K published medical abstracts with labeled data on it. And then we also identify the limitations through other means. And what you see here is just a starter point to show you the limitations can be easily identified with a particular probabilistic score attached to it in a given document. On the mention side of it, we did use the pre-trained models from Chan Zuckerberg Initiative. The PMC articles that were used here just to show you to demonstrate how we can extract out what methods are being mentioned here, what data is being mentioned here. We use BioBert here. It is trained on 36K biomedical research data set, which has already identified 78K method mentions in a pre-trained model. And then we fine-tuned it to do work on our current data. And as you can see here, it is able to identify the RNA sequence, chip sequence method, or PCR amplification method, as well as data attached to it. In the next step, we also do the event measurement or event handling to understand what are all the events available in the given published medical journal. And once again, we use BioBert with 16K published medical data set to predict the events. As you can see, it is still a work in progress, but determining significance events from the literature is a work in progress, but will give you good information to apply on adverse events in the next pipeline. Moving on to the step 2 recognize. Step 2 recognize is basically a biomedical NER work where we recognize the biomedical entities in the given text. Efficiently recognizing biomedical is a prerequisite for doing knowledge mining on the biomedical data deposited in unstructured text. As you can see, we apply different techniques here. For Tagger, we use science Bayesian fair majority of the work. In entity linking, we do UMLS and mesh. And we have seen significant outcomes from BC5-CDR, which is a chemical disease relation, and Bio NLP 13, which is for the cancer genetics, as well as craft. We also do some transformation on the Hearst patterns and enriched it with National Center for Biotechnology Information Disease corpus. On the entity recognition on the science bird, we are able to identify up to 20 types, and it is counting. Some of the types are like anatomy, gene, chemical, disease, protein, organism, cancer, cell, tissue, pathology, taxonomy, you name it. We are able to identify it. One of the things about science bird is it has a set of libraries attached to it, which includes the relation extraction from Chemprot, and as well as Genia, and as well as citation, intent, etc. On the recognize, just to show another example for you from already available published medical journal, just to demonstrate the capability for you. Here we are able to identify each entity, whether there is a risk, whether there is an injury from science large, and as well as understanding the NCT tags and any inclusion criteria that we need to be understanding here. One of the main things for the medical writers and doctors is to apply the inclusion and exclusion criteria to find the relevant content they are looking for to submit a CER. And we use this methodology to mine that data. Another example for chemical disease relation, another task to identify. And as you can see, it is able to easily identify the disease and the chemical associated with it. Just to give you a background on the HUNER side of things, we also use the HUNER to provision the different entities types like cell line, chemical disease, and we did see some significant outcomes from it. We leverage artificial intelligence systematically for the complete data continuum, and that's where the step 3 comes into play. where document summarization is a task of creating a short and accurate summary of text document. Automatic summarization systems seeks to condense the size of the piece of text while preserving the most of its important information, content, and meaning. We tried both the extractive and abstractive methods, and one thing I would say here is, if you want high quality summaries of long sequences of text, start via the extractive step followed by an abstractive, and you will be able to get a better outcome there. One of the things we did in the extractive side is just to showcase you, we use the BERT summarizer here. We can provide minimum length, flexibility of adding a ratio, do elbow, understand the contextual density with optical K in cluster, and we also use the digital BERT for that. On the abstractive summarization, we went for long formers. We will discuss in detail in the next slides. This is just an example of summarizer with extractive for you on a published medical journal, freely available. As you can see, that article is about comparison between two products from famous manufacturers for a particular medical procedure. It captures the essence of the literature through qualifiers like the number of sentences, the ratio, and the dials like optical K-means and minimum length in which you will be seeing the output. We also did a custom trained model here on top of the existing data set and pre-trained models. The ratio of sentences that you want on the final summary can also be tuned here. Moving on to PEGASUS. PEGASUS was presented in ICML 2020. PEGASUS stands for pre-training with extracted gap sentences for abstractive summarization. It's a sequence model. The base architecture of PEGASUS is a standard transformer encoder, decoder. What you see in this diagram is just to explain the gap sentence generation and the machine masked language model are applied simultaneously to an example as a pre-training objective. Originally, there were 3 sentences, as you can see in the bottom there. One sentence is masked and used as a target sentence as the text for GSG, and the other 2 sentences remain as input, but some tokens are randomly masked. And this is the same technique they apply when you apply on a large corpus. It is pre-trained on C4 corpus. In PEGASUS, what we found is the important sentences are masked from an input document, are generated together as one output sentence for the remaining sentence, one output sequence for the remaining sentences, similar to an extractive summary. We experimented with large scale data sets for PubMed and PIC patent. And there is also a possibility, if you are interested in archive journals, that is also a possibility. This is another diagram just to quickly give you an idea of, we trained the PEGASUS on the 215K PubMed articles. And one of the scores that we use for evaluation metrics is called ROUCH, Recall Oriented Understudy for Adjusting Evaluation. It can be used effectively in automatic evaluation of summaries if you have a ground truth with you. There is also coverage and density that you can measure, the fragment coverage, the fragment density, and the compression ratio. This diagram kind of shows you the approach we took to get the abstractive summary from a pre-trained model, as well as how our data model pipeline looks like from all the things that we have discussed so far. I'm just going to jump to what next in this space. What we see is Google has recently released a Big Bird on PubMed. Big Bird is a sparse attention-based transformer which extends transformer-based models such as BERT to much longer sentences or sequences. And I think they have increased the limit up to 16K now. It is with sparse attention mechanism, right? It eliminates the limitation with linear dependency and long sequence encoder task. It works on long formers. We have seen some significant improvement in demonstrating its ability to paraphrase, as you can see on the screen here, the predicted summary versus the ground truth summary for one of those published medical journal articles. Empirically, I think Big Bird gives a state-of-the-art performance on a number of NLP tasks such as question answering and long document classification. And the diagram on the right side shows you some of the details there. On the knowledge mining side of the author and review part of it, we do use Azure heavily on the cognitive search as well as providing question and answer, but we also have some specific cognitive services for translation as well as our own models for translation. The step 4, I just want to emphasize this particular point here. What you see here is one of the bird's eye view or a little thumbnail of a bigger architecture we have built for a language intelligence services in AI. We call it as LISA in HCL, where the documents flows from left to right, where it can be structured, unstructured, PNG, JPEG, PPT, XML, video, audio, anything in enterprise information structured data can flow in. We store them in the knowledge store and knowledge base, which eventually helps the Q&A maker, another tool provided by Azure on top of cognitive search, gives you a human-like parity to understand a paragraph in a document, as well as it provides you machine reading comprehension like a short answer, long answer form to grab the concept part and try to answer the question in a human-like way. So we voice enabled it, and we have a Microsoft bot platform that helps us to interact with our advisor. We call them as LISA advisor. It uses a RNet neural network architecture where it understands the subject, the concept, the conditions, and the predicate. So the when and who part and the attention-based gated model to bring the innovation into any enterprise is what we are trying to achieve here. It is also worth noting that during this journey, we also leverage different storage types and the formats in that journey to make a fully comprehensive approach. We use around 15 plus cognitive services, and we enrich the data and apply AI custom skills on top of it. What you see here is the very next step that we also do some translation work, and we do majority of the translation through AI, whether it is cognitive services or using our Facebook's FAIR M2M 100 models. It is always AI driven. FAIR sequence is a sequence modeling toolkit that allows researchers and developers to train custom models for translation, summarization, language modeling tasks, but we mainly used it for translation, many-to-many multilingual translation model. The diagram here kind of shows you a published medical journal being translated from English to Japanese and Japanese to French, just to give you an idea. If you want to try faster processing, we highly recommend using Apache Aero and Apex. As you can see from the highlights there, you can pre-process, apply sentence piece to it, do the Moses decoding to it. You can distribute it. If you have an NVIDIA V100 boxes sitting with you, you can do model parallelism to it. And our opportunities for distributed model training with FAIR scale was immense. Thank you. Next on the human in the loop. This slide is a very important slide. Whatever you do, even if you think you are a data pioneer, we think you need to be a data practitioner first. And the reason is then only you can augment the AI in the workflow. For example, the classic example I showed you earlier, as you can see in the diagram here on the don'ts, limitations, even if you miss one for a given medical device, it is problematic. So your human accessor definitely need to be in the loop. But we also see that ROUGE and BLU scores as guide to ground truth, and as well as plain data set is probably the best thing to start with. One of the major challenges for us is finding sample data. And the key takeaways from the first use case of intelligent clinical evaluation is by applying all these AI techniques, we are able to significantly reduce the cycle times, leading to reduction in cost as well as increased cycle times, right? Decreased cycle times. There is an information advantage, and then there is the decision advantage. So if as an organization you are able to bridge the gap between the event happening and the action, and this timelines can be dramatically decreased if you apply AI to it. We also see this as an automation opportunity in many cases. I just want to move on to the next use case, contextualization. And I just want to take a moment to give a better frame of reference here. As you saw it, the fundamental building blocks of NLP, NLU is applicable both in intelligent clinical evaluation and contextualization, but contextualization has a larger net. And this is especially for a Aero customer, where the ask was to contextualize the given information as part of the digitalization journey, where they have information spread all across the organization. But this particular use case is applicable not just for Aero, but also for auto, insurance, financial, industrial, manufacturing, and many others. So in the second use case, we are going to just expand on a bit for you to show you how to unpack the customer ask and apply the AI solution to it. What you see here is similar to what we have discussed earlier, if you recollect. Again, if you see the classify, recognize, intelligent, there is a bit of a difference here where you should be in a position to link artifacts in the recognize phase. And as well as in the intelligent phase, you should be in a position to apply a domain AI to it, given whatever the domain you are working with, and then bring the machine reading comprehension, the short answer aspect of it, and the ability to automate and apply AI search skills with a advisor kind of setup where you can give them a specific response. For example, in the Aero case, the customer wanted the interaction to happen between the shop floor to top floor. In everyday work, the service engineer, the designers, the design artifacts, and other data people, service data people, right, are scattered around the organization. They interact with each other to find the needle in the haystack when they try to find the information. But how about the information comes to them? And that is what we attempted here. And I'm going to step back a bit to make a broader point. What you see on this slide is mostly the same of what you would have been seeing for auto or industrial or any other particular domain. The idea here is to understand the differences by the domain and apply the base foundational NLP, NLU technique, irrespective of the environment you are working with. So moving on to the next slide, I'm just going to go deeper into the contextualization part. Here, as I mentioned, as a Aero customer, had multiple design artifact, design diagrams about specific parts, Aero parts, and then the information in XML were majoritarily on the BOM requirements and the task and all. And then they had PDF for specific service manual instructions and other documents, and then certain documents and XLS for particular part numbers and other details. And how do we combine all this information and provide an AI-driven solution so that it helps them to contextualize the task that they are working with and able to easily identify the documents they need to work with, and as well as identify the detail of the task that they need to work with. We leverage cognitive search for this. We applied Q&A maker on the service manual. We also identified the metadata that connects the dot between the design, the BOM, the service manual, and the task. And in that journey, we also saw that the Aero customers or the Aero suppliers are all over the world with multilingual translation is a basic need there because majority of the documents are in English. So how about a native Spanish speaker talks to the document in the native Spanish language, but still able to understand and get translated English to Spanish? And that is what we attempted here. In the contextualization journey, as I mentioned earlier, right, I just want to highlight a couple of factors here. As you can see here, BERT is still the BERT. T5 is used for question answer paraphrasing. Named entity recognition was used to identify the design artifacts and the service manual specifications. And then we also use something called CDSSM from Q&A maker. Convolutional deep structured semantic models are used for sentence level semantic matching. This is a dual encoder model that converts text strings like sentences, queries, predicates, and mentions, etc., into their vector representation. And then you can use that with the query and answer are vectorized from a cosine similarity between them, and it's computed to give the relevance of the answer to you. Q&A maker task on a domain-specific data set, we see significant improvements on any domain that you work with, as well as we use the T5 for paraphrasing the questions. If you notice it, traditionally the TF idea, the term frequency, inverse document frequency, futurizer with global inverse document frequency to disambiguate the knowledge base specific data was used. But now with the CDSSM, we see the active learning is a possibility here. On the other side, on the right side, I just want to emphasize on two things. We also used M2M100 for multilingual translation and Wave2Vector2 for speech to text when it comes to voice recognition and converting that speech to text in multiple languages. With that, I'm coming to the reference slide. I just want to thank you all for joining this call, and I want to give two shout out for at least 2 or 3 references here. We used Alan AI ScienceBird specifically for majority of our tasks in terms of NER, and PEGASUS model for summarization, as well as BioBird and transfer learning for text-to-text transformer. Thank you. If you have any questions, please feel free to ask. Thank you.